careful about that. So, so for example, if you're supposed to like enter hello and you did hello space, we can account for that in Mimir. But if you do hello space in Canvas, it'll be like, no, that's wrong. So watch out that you don't enter in any additional white space in your answers. So be careful with that. The ones that pay like special attention to in terms of like finickiness are the ones that ask you to write the debugger code to print out like values on the stack or values in registers. They're just a little bit more picky about what they can accept, and putting in additional options is more complicated there. So that's why it's more strict. Most of the quizzes are due on the last day of instruction, which is the 13th, so a week from tomorrow. And then the final is due on the 19th. You know enough to be able to do all the quizzes and all the midterms that are there. You don't know enough to do the final yet because we're still talking about some of the topics. Are there any questions before we get into lecture though today? Yeah.
I have a question regarding the quiz. Like apparently like for some of the instructions where we have to like manually implement them, like first person EX, even if I like follow the instructions you have like given on the slides, it won't like give me the answer. And the same goes for like question number 14, which is doing like calling the function, but it works for the opposite. Like the return works well and the pop works well.
So stop by office hours and we can take a look over those questions. Someone did post about this on Canvas, but their answer that they had for like push was push.
Oh no.
So I'm like, well, it kind of makes sense. But the question that asked you to implement push, and your answer was push is not correct because you got to use other instructions. So that was the person that mentioned that was the only problem that I saw with their answer. But if you're doing the correct stuff and you're showing me that you know how push is actually implemented, stop by office hours today. We'll take a look over the questions and we'll see if it's either a problem on the testing end or a problem with your answer. If you do have like additional, like don't leave extra blanks in there. Take those out because you might be counted against you for that.
Right. Okay.
Yeah, Haley?
It's probably on the syllabus, but it's not a thing that you can drop one homework. Is that a thing?
And no, I do not drop one homework. Yeah.
Are there any more coding assignments after homework 4?
No. There are no more coding assignments after homework 4. So originally the problems were all on Canvas, but again, their input format's a lot more finicky. So we were trying to do the conversion from the Canvas questions to Mimir to allow you to have more flexible input and be better able to match answers or handle like small errors in your input. But the TAs didn't have enough time to do all the conversions for everything, so we had to fall back and use the Canvas ones that I had already done in previous quarters. Anything else? Yeah.
Are the Canvas ones limited attempts?
Yes, they do. They have like 3 attempts a piece for the most part. Anything else? Generally, my recommendation is try it once. If you get it wrong, go look up what you got wrong and then try it again. And then if you still get it wrong, come to office hours for help. One of like the downsides again of like the Canvas is like if you miss one question and you want to redo it, you have to redo the entire quiz. Yeah, which is again one of the reasons why we're converting things over to Mimir, because it would just let you redo the question instead of redo the entire thing. Anything else? Okay. What are the GCC seat calling conventions? This tends to be one of the biggest mistakes that I've been seeing in office hours. So what are our 3 rules? Return values are placed in EAX. So the calling function, right, it's responsible for saving EAX, ECX, and EDX. The function that is called is responsible for saving all of the other ones. And the last one has to do with how do you get arguments. The arguments are placed on the stack, right, and they're pushed in reverse order. So the functions that you're writing, are you the caller or are you the called function? caller. So you're the function that's doing the calling. You are the called function. You are both. You're going to be both, right? Because we have something like, maybe over here, right? Because we have something like function 1, right, calls function 2, calls function 3, right? You're essentially a function 2 in terms of that sequence, right? My main code is going to call your function, and your function is likely to call other functions. So when your function is called fun2, it's responsible for saving what registers at the beginning of its running. So fun2, when it's first run, what registers is it responsible to save, assuming that it wants to use all of the registers? So is it EAX, ECX, and EDX, or is it everything else? So is it A, C, and D? Everything else. But your function 2, you were just called. You are the called function, right? The caller was function 1. Function 1 was responsible for saving A, C, and D before it called you, right? You are the called function, so you're responsible for saving everything else at the beginning if you're planning on using it. So function 2, at the very beginning, right after you do your prologue, you would want to save like ESI, EDI, EBX if you're going to be using ESI, EDI, or EBX, right? Now when function 2 calls function 3, what registers is it responsible to save? A, C, and D, assuming that it's using them and it has values that it cares about them, because at that point it's the calling function, and the calling function is responsible for saving EAX, ECX, and EDX, right? A lot of you guys were getting this like the other way around, backwards, so pay careful attention to that you're following the rules. I think they're pretty straightforward as to like what they mean, right? But the implementation details are also supposed to be straightforward too, right? Like return value, put in EX. When you want to call a function, you push the arguments. Push them in the reverse order, right to left. When you get called, if you want to use EBX, ESI, or EDI, save them, right? When you call something else, if you have anything in EAX, ECX, or EDX, save them first, then do the call.
I have two questions. So if you don't need any of that stuff though, do you still have to save it?
So if you currently, like, can you be more specific by that stuff?
So like you use those registers previously before calling a function.
Which registers?
EAX, EDX, or ECX. You
Okay.
used it. And then you call some new function. And let's say, yes, you want to save those values because you need them later, but let's say you just use them as like a temp before the call, then you still have to.
So if you have things in A, C, or D that you don't care about, you don't have to save them because you don't care about them, right? So if you have values in A, C, and D, right, temporary things that don't matter and you're okay with them being overwritten, you're no longer using them, sure, don't save them, right? But if you have something in those registers that you care about and you still want to be able to use those values after the function call completes, save them first.
And then I'm also confused about when you push something on, when you're pushing the actual thing, or if you're pushing when you're pushing a copy of the thing. Like how you can modify like, the reference.
So you're always pushing copies.
How do you push not a copy?
You can't push not a copy, right? But if you're talking about C++, how can we like, call a function that accepts a reference? Is that your question?
Yes.
Right? So how could we like implement something like this if I have like my function and it takes like an integer reference, A, how could we implement this? Right? So let's say like in this function we do something like A is equal to 5, right? Something very simple along these lines, right? If you had to write this function in C, how would you do it? Not in C++ anymore. You're forced to write an equivalent, or as equivalent as possible, a function in C. right? This function, its signature would be like, fun1 in the C version, and it's going to accept an integer pointer, right? A. And then down here, you would have to say star A is equal to 5. So the way that references are implemented is they're like ninja pointers, right? They're just pointers in terms of how they're implemented in the back end, but you just don't have to dereference them when you're working with them. And then you don't have to pass the address of when you call the function, right? If we were going to call, if we were doing the same thing over in the C code though, we would do like int x equals 7, and then call fun1 though with the address of x.
How do you push that on the stack?
How do you get x's address? Yeah, you can use leal to get x's address. Or again, if you had something like this, like integer pointer p is equal to the address of x. I mean, you'd still have to get the address of x. You could also just pass in p here, and that's the exact same thing. Right, you'll get the same effect. Right, the reason that this works, right, you get the real object with the pointer is because if x is stored at address 100, right, you would pass in 100 as the address of x. How many addresses 100 are there in the computer? 1, right? So everybody's going to talk about address 100, which is at one exact spot in memory, and so everyone deals with the original as opposed to dealing with a copy, right? But the function, right, when you call it, it gets a copy of the address, which would be 100. So a copy of 100 gets placed onto the stack, right? The 100, right, is a pointer. It's a value. Its value is 100. And so when you push onto the stack, right, like P, or you push onto the stack the address of X, really all you're putting there is 100, a copy of where the thing is located at in memory, a copy of the address.
Okay, but then let's say you have an integer pointer to a list of items, and I'm confused when you want to pass that whole list. You want to push the whole list on the stack. Like, when do you have to put something in a register and then push it, and when can you just push the name like blank past EBP?
So you could always do push blank past EBP if what you wanted to push was the thing itself, right? So if you wanted to push X, you could say push X past %EBP, assuming you had X, regardless of whatever X's type is, assuming that when in your C code, you were trying to call the function with X, right? But if you want to do X plus 1, well, then you got to copy X into a register, add 1 to it, and then push it, because when you call the function with X plus 1, you don't change X, right? The adding of 1 shouldn't modify X. So you couldn't do something like add L1 to X, because that would be X plus equals 1, and then X would be modified.
So you're saying if you had C is equal to 1, 2, 3, 4, 5, and C was in EBP, and you push C, is it pushing 1, 2, 3, 4, 5, or is it just pushing the first location?
It's pushing, again, it's like if your function accepts, think about what your function accepts. The function accepts an integer pointer, right? So you would be passing one address, right? The address 100, which is where the beginning of the array starts at. Because if you think about it, if I know where the array starts at, I'm great, I'm golden, right? Because if I want to access the element at position 100, I can do like, array at 0, and that's going to give me memory at location 100. But if I want to access the next element, well, that's array at 1, which we do array 100 plus 1, 101 dereference to get the second element in the array. And this is why it's important that the elements in the array be contiguous. They have to be next to each other in memory. Otherwise, this breaks apart and no longer works. Does that make sense? So really what you're pushing when you've been thinking, I push the array, really you're just pushing the address to the first element in the array. And then, well, great, that array starts at location 100. And so when you dereference it, you're going to go to location 100, which is where the array is at in memory. If we do array at 3, we're going to go 3 past 100, right? And then access the element that's there, and hopefully that's still a part of our array, and we'll get the element at index 3.
So if you're pushing blank past EBP, so that's like a,
Yeah, some label.
Are you getting the address of a copy of that array, or are you getting the address of that array on the stack?
You're getting a copy of the array's address.
Okay, so it is like the original on the stack item.
You get a copy of the array's address, right? So over here, let's say again, address of X is 100, P is 100. And now when I do this call, right, I'm going to be pushing what onto the stack? 100, which is a copy of X's address. Notice that P itself, if inside function 1, right, we did something like this. Oh gosh, come on. Like A is equal to 500. After we do this call, right, what's the value of P? Right, again, if we said in our example the address of X is equal to 100, what's the value of P after the call is complete? How many of you guys think it's 500? How many of you think it's still 100? How many of you think it's something else besides 100 or 500? Because again, think about what happens under the hood when we're doing this call. I got to get rid of all these extra spaces, right? So let's assume that we're trying to implement this little section of code and calling our function, right? And again, assume that we have like P past EBP, right? So in implementing this, we could just do something like push P past %EBP, right? Call fun1. And again, if we want to get P itself, right, we could do something like leal X past EBP into say %EAX, move L %EAX to P past EBP, right? This is EAX is equal to the address of X. This is P is equal to the address of X, pushing the argument, calling the function. Is X in P? No, what's in P? Not X, but the address of X is in P, but P itself is not, right? And again, you could never even put P in or X into P. You could only put a copy of X's value into P because they're two different memory locations, right? You can't force them to be the same thing, right? You can say 2 pointers point to the same location memory, perfectly fine, right? But memory locations are unique, and you can only have copies of values at different spots. So if we're now doing this over here, and we're over here in fun1, right, here's our label. So here's fun1, right? And, you know, we do like push %EBP, move L %EBP to %ESP to %EBP, right? So after we do this, what's the stack look like? EBP is pointing to, right, old EBP. So that's at +0. Above old EBP is going to be, right, the return address. Above that is going to be, well, the address of X, but again, like if we think about what we got called with it, it's A, right, because that was the name of the variable. Again, back here, we called it A, so we have A. And then if we think above that, we probably have something like P and then X. Right? They're different locations in memory. Right? So our function fun1, who's he going to mess with? Our function fun1, who's it going to mess with? A, right? So in terms of like implementing this code, right, if we wanted to do exactly what it says to do there, we would do something like move L A past %EBP, 2 words, right, past EBP to maybe EAX, and then move L $5 to percent EAX, right? This is EAX is equal to A. This is star A is equal to 5, right? Which was this first line of code that we want to do. Now we want to say A is equal to 500. So you move L $500 to where? Again, we're trying to do A is equal to 500. So I would move 500 to A past EBP, right? The function then completes. We're done, right? So remember, X, when we started at the beginning, X had the value like 7 in it, right? P had the value 100 in it, and A had the value 100 in it. After we do this line of code right here, this says go to wherever P points to, right? Or wherever A points to, which A is pointing to address 100, which is where X is at, right? So this is going to change the value to be 5, right? The 7 is going to go to a 5. Then we do move 500 to A, so A goes from 100 to 500. The function then cleans up, right? So it's going to like, we return, right? All the arguments get cleared up. So we're going to remove A. What's P's value still? 100. P didn't change, right? And we can't change P because we only get into this function a copy of P's value, right? You always, 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 always pass copies. You never pass anything else. So if you change the copy, the only thing that's changed is going to be the copy, right? Whether that be a copy of a pointer or a copy of a non-pointer, the only thing that you get is the variable itself, or copy of the variable. So you can only change the copy. Right now, if you get a pointer, you can go to where that pointer points to and change what's in that memory at that location, and it will be modified. And since there's only one location for each address, if everybody's talking about that same location, that one location will be changed. Yeah.
You referenced A past EBP, but it didn't look like we pushed that on the left side.
But no, we pushed P, right? Because P was supposed to go into the spot for A, right? So we pushed a copy of P's value should be put into A, which is what we did, right? That's what this line of code right here did, right? Call your function with P's value, right? P's value was 100, so we put a copy of P's value on the stack.
So the only actual thing like on the stack on the right-hand side are like EBP red address.
Well, I mean, our function, right, function 1, it's only going to care about these things. It's never going to talk about anything else, assuming it's written correctly. So even though, yes, on the stack we have X and we have P, function 1 has no idea about that, right? Or at least it's completely agnostic of the fact because it never knows where it's going to be called or what it's going to be called with. So it's only going to reach for its arguments, right? If you pass a copy, though, of one of the locals, right, the local from the function above is still going to be on the stack but above you, but you're never going to look there, right? Unless you're passed an address and you're told to go to that address and modify the value like we were able to change X from 7 to 5. Anything else? Yeah.
We actually do move 500 to isn't what number has to be
So what's the rule on the limit for the memory operands? You can have at most one operand in memory. So if you look at that instruction, A past EBP, that's in memory, but 500 is a constant, which is not in memory. It's not a memory access, so you're fine, right? You just can't have two memory accesses. So one of the other things always has to be, if you have one thing as a memory access, the other one has to either be a register or a constant. Could not be another memory address. Anything else? Okay, so we'll pick up from where we left off. I'll just leave that at the bottom of the presentation. So last time, right, we talked about how an application gets loaded, right? Do you remember what the steps are to make that happen? Right? These are types A.out in the terminal. What's going to happen next? Say it again? Not find it in memory, right? It's okay to look at your notes. That's hopefully why you took them. What? Well, we'll do EXECVE of A.out, right? That says operating system, please go run the program. So we say operating system, run the program by making a call to EXECVE, right? So now the operating system's running. The control got turned over from the terminal to the operating system. What's the operating system have to do next? Again, you can think logically what would have to happen, right? Where is A.out currently located? A.out like bob.txt or funnypicture.jpg or cool.gif, right? Those are all what in your computer? They're all files, right? But your program, it's also a file too, right? It's just a file that contains instructions to run, right? That's all the program is. It's a file that contains instructions for the computer to run, right? So where are files kept at? On the hard drive, right? So you want to run A.out, it's currently where? It's on the hard drive. So what do you have to go do? Go find it on the hard drive. Great. You've now gone and you found it on the hard drive, which take the operating systems class and they'll tell you how that's actually done, because that's a big step in itself. Right? So you found A.out on the hard drive. What should you do next? We have to find space for it, right? How do we know which space is available? Yeah, the operating system has memory tables that keep track of which spots in memory are free and which spots in memory are in use, right? The operating system is able to do this because the operating system is what manages the memory, right? It's the thing that's always allocating memory for all the other programs or all the other processes that need to be run. So you need to look for a spot in memory, but it needs to be big enough to what? Fit your program. But how big? How do you know how big the program is? You read the headers, right? So you read the headers, and they'll tell you like how big the program is, right? It's going to tell you where is the start. It's going to tell you where the text section begins at. It's going to tell you where the data section begins at. So great. So you know how big it is. You found a location big enough in memory to hold it. What do you do next? Not quite, right? Because all we know is this spot in memory is big enough, right? I have my program. It's still on the hard disk. So what should I do? Copy it over. Great. So we've copied it over. Now the program is in memory, because when programs are running, they are in memory, right? So they're in memory right now, right? And so even though it's in memory, is it currently running? No, right? How do we know it's not running? The OS is running. And what's it mean for a program to be running? The instruction pointer is pointing to memory that belongs to that program, right? So what do we have to make happen if we want to be able to run the program? Set the instruction pointer to be equal to the what? The start of where your program is, which again, you know where that is because you've read the headers. So you can jump to the start of the program, but what happened was you were currently doing something, right? You currently had some state saved in your registers, right? If you just go and run that program can overwrite your state, and it probably will, right? Currently, the stack pointer is set to the operating system stack, so that program could overwrite that area in memory too to make it do something that it shouldn't be doing. So before we go and we jump to the program, what do we have to have happen? Say it again? So before we wipe the registers, we should save them, right? We should then go wipe the registers. I agree. So we can wipe EAX, ECX, and EDX, but we should also set ESP to point to A.out stack, wherever that begins at, right? So set A.out stack to wherever it's supposed to begin, wipe our registers, and then we can do the jump. Hopefully this series of steps makes sense to you and doesn't seem enormously complicated or overly detailed, but it should just be a logical consequence of what do we want to have happen next, right? What do we have to make happen to run the program, right? We have to go find the program, right? Put it into memory at some spot that we can hold it, save our own state, and then start that program up, right? Which should hopefully make sense in terms of what we need to do. The other thing that we talked about was the operating system. Like we discussed, it's a program, a big, complicated program, right? But it's a program. But if the OS is the program that loads programs, how does the operating system itself get loaded? Yeah, the bootloader, right? What's different about where the bootloader is stored in terms of programs than normal programs? The bootloader is stored in ROM, right? That's important, right? This resolves the chicken and egg problem, right? As to who comes first, right? So we go and we have our bootloader stored in ROM, and so when Intel is turned on, EIP will be set to this weird address. So you make sure our bootloader is there, right? The bootloader is just going to go and grab that first sector of the hard drive because it needs to be a small, simple program, and it's going to copy that into memory. And then it's going to go jump to that location in memory and start running that program that it just copied in there, right? It turns control over to that. What the operating system will make sure to do, because it wants to be the first program that's run, is it's going to put itself at the first sector of the disk. Right? And so it was going to go and run your OS, and your OS will load the rest of itself in. And then your OS is running, and then great, you can go do everything else that you want to with your computer. Does this process make sense? Now, some of you guys might dual boot, right? You start up your computer and you can choose, like, do I want to boot into OS X, or do I want to boot into Windows, or do I want to boot into Linux? How do you think that's accomplished? Bootloader, sure. I mean, but the bootloader, all it's going to do is it's going to read that first sector of disk into memory, right? Jump to it and run it. Say it again. I mean, the OS is a file, right? So sure, but how do we make it so that the the program that lets you choose which operating system you want to boot into is the first program that's run? No, that would be trying to change what's in the bootloader. We don't want to change the bootloader. But what's the bootloader always do? Sector of the disk in memory, right? It's going to be a lot easier to change what's at the first sector of the disk in memory than it's going to be to change what's in the bootloader itself, right? So what you could do is you could move your operating system from the first sector of the disk to somewhere else, right? And then go put your boot chooser, I don't know what you want to call it, your boot chooser program at the first sector of the disk in memory. So when the bootloader goes and copies the first sector in, it runs the program that's going to allow you to choose which operating system that you want to boot into. That program needs to save where it's moved all the other operating systems to. And then what it can do is it can just go jump to that sector of the disk in memory, copy it in, and then run it, and great. You're now running Windows or running OS X or running Ubuntu, depending on which other sector of the disk you copied into memory and then ran. So it's not a much more complicated process. It's just now there's two stages, right? Put the boot chooser at the beginning. The boot chooser then will go load the appropriate operating system. And a lot of times these bootloaders actually do run at multiple layers where they keep loading progressively more complex programs into memory to finish loading the rest. So you might actually have like 2 or 3 stages of bootloading to actually get the entire operating system into memory and it to be running. Are there any questions about booting the operating system? Okay. Let's talk about our next topic then, which I believe is time sharing. So time sharing is just, let me see, make sure I get the right term. Nope, not that. Yeah, okay, it is time sharing. So time sharing is just multiple processes taking turns so quickly that it appears that they are running simultaneously. The key word here is appears. So have any of you guys ever like watched Dragon Ball Z? Right? You know the parts in Dragon Ball Z where the guys like move around the other guy so quickly, right? That it looks like they've completely surrounded the bad guy and they're all of those positions at once, right? But are they really at all those positions at once? No, right? They're really just taking turns being at each spot. But because they're going so fast, right, between each and every spot, it looks like they're in every spot simultaneously. But they're really not there. They're just moving really, really quickly. Or another way of thinking about it, if you guys don't watch anime, is you could think about a light switch, right, and a light bulb. If you take that light bulb and that light switch and you flick that switch really, really, really rapidly, what's it look like if you're able to go quick enough? Does it look like the light goes on, off, on, off, on, off, on, off? If you go really, really fast, what actually happens? What's it appear to your human eye when you're detecting this phenomenon? What? Just speak. I was just having a hard time hearing you. It's like it looks like it's always on, but will it look the same as when it's just fully on the whole time? It'll be dimmer, right? The light will not be as strong. And if you actually have LED lights, that's how they work when you have the dimmer switch, right, on them. They don't really just get less intense. They just start flashing really quickly, and so they're on, off, on, off, on, off. But to our human eye, it just appears like the lights got dimmer, right? The same concept is here, right? It's not really that the light got dimmer. It's really that it's going on, off, on, off. It's not really that the programs are running simultaneously. It's that they're taking turns really, really, really quickly, right? Does that make sense? That's what time sharing is. So in time sharing, processes are given a time slice, or also quantum, to run, right? To give you an analogy, maybe each program has 5 seconds. So your time slice or your quantum would be 5 seconds. So we run program A for 5 seconds. Program A then finishes, and we run program B for 5 seconds. Then program B finishes, we run program C for 5 seconds. Program C might finish, we go back to running program A for another 5 seconds. These time slices are actually going to be a lot smaller than 5 seconds, right? Probably like on the order of milliseconds in terms of how frequently they run. So to us, it still looks like they're running simultaneously, but you get a small amount of time to run. Does this make sense? Oh, we may have accidentally skipped a topic, but we can go back to that one. So the way that this is implemented is there is a timer that goes off every, say, X seconds. This timer goes off more frequently than a time slice. So let's say, for example, that the timer goes off every 1 second, but you want every program to run for 5 seconds. How do you make that happen? So again, the timer goes off every 1 second, but you want every program to run for 5 seconds. What? Well, no, it's always going to go off every 1 second, right? Maybe your alarm goes off at 7 a.m. every morning, right? But do you get up? No, what happens? Hit the snooze, right? The alarm goes off again. Then what happens? Hit the snooze button, right? It goes off again. Hit the snooze button, right? And then, finally you might actually get up, right? In terms of what's going on. But can we have that happen, do something similar when we're writing our program, right? The alarm has gone off, right? And you know that it goes off every 1 second. But we also know that we want our program to go off, to run for 5 seconds. So the alarm goes off the first time. The timer goes off the first time, right? How much time has passed for this program? 1 second. So has it run for 5 seconds? No, so what should you do? Like, start that program again, right? Kind of like, count the fact that the timer has gone off. It's gone off 1 time, right, for this program. Then you're like, well, okay, well, fantastic. I count that. Program, continue running. Timer goes off again. It's now gone off 2 times. So we ran for 2 seconds. So mark the fact that it's gone off for the 2nd time. Continue with the program. It's gone off the 3rd time. Again, mark that it happened the 3rd time. Continue the program. Mark that it happened the 4th time, right? Continue the program. Goes off again the 5th time. So we now the program's run for 5 seconds. So what should we do? Stop that program and then run the next program, right? In line. Stop running program A and then go run program B, but then set program B's timer to be, or like timer count to be 0, right? It's not like a very complicated thing that you have to do. It's just think about it. It wants to go off for 5 seconds, right? But it goes off every 1 second. Just mark the fact of how many times it's gone off, and when you're ready to change, enough time has passed, switch to the next program. Same thing happens inside the computer, right? So we might want the time slice to be y seconds, right? So when the timer goes off, right, timer count plus plus, right, it goes up by 1. Then when timer count is equal to y over x, something like that, or like something along those lines, right? Yeah, that makes sense. Then switch to the next process. Do you guys know what the difference between a process and a program is? So just here, a process is an instance of a program, right? For example, right, you might have Google running, right, Google Chrome, right? That's an instance of the program Google Chrome. But how many Google Chromes can you have open? Quite a few, right? Look at my tabs. Right? So every time we want to have like a new instance of Google Chrome, right? A new process, right? We go and start it up. So you can have multiple instances of the same program running, right? With different data doing different things. So a process is just an instance of a program. So if we're thinking about time sharing, right? How would we want to implement it, right? How would you go and decide to do it if you were responsible for implementing this part of the operating system? Right? Assuming that, right, at this point in time, A, or process X was currently running, and its time is now over, and we want to switch to process B. Again, think what would be your strategy for solving this problem, right? A's turn is over. We now want to run B. How can we make that switch happen? Yeah, it's going to be very similar, but right, there's going to be some differences. So we have process A is running. We want to switch to process B. How can we do that? What would your first step be, right? Just got to take it step by step. What makes sense to do? Talk with your neighbor for 2 or 3 minutes and see what steps you guys come up with to saving it, right? What things would you have to do to make that switch happen between the two processes? Okay, so you guys have some thoughts. What would your first step be if you wanted to switch between these two processes, between X and Y?
Is it the same instance? Are there two different instances of the same program?
Do you care? Does it matter? It doesn't, right? Right? It's because you're going just from one process to another process, and you're kind of agnostic whether that process is a different, is if it came from a different program or it came from the same program. Doesn't really matter. It's just that next process's turn. Right? Because again, like if you're running 2 instances of Microsoft Word, right, and you're writing in one, right, and then you want to, the other one should still be writable, still be accessible. Does it matter whether it's Microsoft Word for document A or Microsoft Word for document B? Or does it matter that it's Microsoft Word and like YouTube? No, you just want to switch between the two. Hopefully. Right? Because again, like you don't like the operating system, yes, it knows in some ways which program they came from, but in this case, we don't really care, right? You just want to switch from that process to the next process, and knowing whether they came from the same original application or not doesn't matter in terms of doing the switch. So what should you do in making that switch between A and B, or between X and Y?
Just save for last.
Right, so we need to save X's state, right? What is, so we'll come back to that. So we save X's state, then load Y's state, and then start Y, start the process. Right? Which hopefully it seems fairly obvious as to like what should go on, right? Save the one that was running so that we can run it again in the future, right? Take the one that we want to run, which we must have saved it previously in the past, put its state in there, and then start the program, right? So what's the state of a process composed of? What things are you going to have to save? So you want to save that entire program's memory? But again, that stuff, right, that the program itself is already in memory, right? As long as you don't replace what's in that location in memory with something else, it's still going to be in memory, everything that it had there. So all of its text, all of its data, all of its stack, all of its heap is still going to be there, right? Because you already put it into memory, right? And hopefully process X and process Y, they're not sharing that same space. Because that means like X would be overwriting part of Y and Y would be overwriting of X, and then things aren't going to work well if they're overwriting each other's memories. So they should be in two distinct separate areas of memory. So you don't have to save what's in memory. What else? So yeah, you'll have to save its location, but the operating system kind of already knows where its location is because it put it there. So it's not a thing that's necessary to save. What else is there besides the program's memory that you might want to save? Again, but the locals are stored in memory.
Wait, so when you say switching between buses, are you just like, for example, having one Microsoft behind you and one in front of you?
So like clicking between them, like giving them focus, doesn't cause this to happen. They're all actually running simultaneously, right? But the one that you might not have in focus that you're not working with right now, it might decide to immediately end its turn as soon as it started because it knows you're not working with it, right? But if it has some other work to do, it might do something, right? Because if you think about it, if you have like a YouTube video playing in the background, right, it's still running even though you're working in Microsoft Word. So they're still taking turns. But again, these turns are so fast, it looks like they're running simultaneously. So what else is composed of the program state aside for its contents and memory? Yeah, I think I heard somebody say it. It's registers. You need to save the program's registers. Right? So you need to save its EAX, ECX, EDX, ESI, EBI, EBP, ESP, EIP. You got to save all of them. Right? Because they're all currently going to be used by that program. Right? So you save that process's registers. All of them. Where should you save this state to? Right, you got to put it somewhere. What makes sense to put it at? In memory, I agree. Where in memory would you want to put it? Not necessarily on your stack because you don't know when you're going to be called again. Because notice neither program is running right now, neither X nor Y. So who's running at the moment? The operating system. So we probably don't want to put it on the operating system's stack because we don't know like when the next program is going to be run. Right? We keep pushing and pushing and pushing. We keep switching programs, but then how do I get back to, if it goes A, B, C, D, right, and then goes back to A, how am I supposed to get A's information if I don't know how many programs we're running in between? So somewhere probably else besides the stack. So a register file is just a name to refer to the collection of registers in the CPU. Generally the data register. So like the register file for like Intel would be like EAX, ECX, EDX, ESI, EDI, EDP, right? But that's inside the CPU, right? We're trying to save that information. And we need to put it somewhere else. I agree it needs to go to memory because it can't be saved in the registers because process Y is about to go use those. But where in memory makes sense? What? I agree in RAM, right? But we kind of have to be able to make this system work, these processes running it multiple times, right? We might need to have some additional information set aside to make this whole scheme work, where we can have extra programs run, right? Like if you were implementing this, what information would you want to store and how would you store it? Again, if you had to say like, I have some set of processes that are running and they need to take turns. A, B, C, D, A, B, C, D, A, B, C, D. Great, B is done. A, C, D, A, C, D. Great, A is done. C, D, C, D, C, D. Oh, great, now we have a new process, E. C, D, E, C, D, E, C, D, E, C, D, E. How would you make that happen?
Are there already labels in memory that are like allocated for its purpose?
Not unless you make them.
Can we make them?
Absolutely. Right? So we're going to save X's state in X's entry in the OS's process table, right? So the OS maintains a table per process where we can go store this information, right? It'll have things like the process's ID as well as the process's state, probably what application it originally came from, right? But all that information will be stored in this table. So you go and you locate X's entry, wherever entry X happens to be at, you go toss the information there, right? Just copy over all the registers. Well, then we need to load Y's state. Where should we get Y's state from? From Y's entry, right? In the OS's process table. Right? So then how do we start Y? Right, again, because again, just loading the state, again, the state is just registers, right? Go copy all the registers back. Right? What register is going to cause us to go pick up running Y? What? Not the ISP, because your ISP is your internet service provider. But you have some of the right letters. You have like 2 out of 3. And 2 of them are in the wrong order. The I and the P are right. And the I and P stand for instruction pointer. Then in Intel, that's referred to as EIP, the extended instruction pointer. Like what really happened, and I'm not quite sure why they did this like naming convention, is like when you have like there's register A, right, which is the 1 byte quantity. Well, the X in AX stands for extended, and then the E in EAX also stands for extended. So it's like the extended A, which is kind of weird, but yeah. In memory, right? So as part of like the operating system's program, right, it will have reserved a section of memory for itself to put for its process table, so they can put processes in there. It is a fixed size, so it limits the number of processes you can run simultaneously. Right, it might be fairly large, right? So infinite, but not quite infinite, but big enough to fit the most normal average case of maybe having like a few. I don't know, a few dozen running. It tends to be the norm. Maybe it's just like 100, maybe 200 big, but probably not more than that. But it doesn't really tend to normally need to be that big. So we need to start Y, right, which is just, setting EIP back to the instruction that Y was on. Now, one of the things that we haven't talked about, which is going to be our next subject, is accessing EIP. One of the problems with accessing EIP is it's not a programmer accessible register. You can't just say move out EIP to EAX, or move L EIP to some location in memory, or take some location in memory and save it, right? The other thing that's kind of interesting to think about is if we want to save X's state, we have to save X's registers. One of those registers would also have to be EIP, right? But right now, are we running X? No, we're running the operating system, right? Because the operating system's the one doing the switching. So where is EIP currently pointing to? The OS, right? So how can I get what X's EIP is, right? That seems to be a problem, right? Because if I'm running the OS, how do I even know what X was doing last? Another thing that we kind of also talked about was when a program is running, it's running, right? And that means nothing else is running, right? And we talked about there's two ways that a program can relinquish control. One is voluntarily through a system call, which we can't guarantee that's going to happen within our time slice, right? That our program's going to make a system call, and so then allow us to be able to switch, right? The other way that we talked about was through interrupts, which is something that we haven't discussed next, but they're actually essential for making this happen, right? This time sharing is not possible without interrupts, which is going to be part of our next conversation on I/O. But before we get to that, do you guys have any questions about what the operating system does for you, or what things we talked about in a little bit more detail it can do or does do? Right, like the main thing to kind of get from about the operating system is it's just at mostly at the end of the day, it's kind of just like a resource manager, right? Your computer has a finite amount of physical resources, CPU time, right? Memory, hard drive space, access to the keyboard and the monitor, right? And all those other things. The operating system's job is just really to make sure that every process gets fair access to those resources so that that process can complete, right? So make sure each process is able to get some CPU time, is able to get some memory, is able to get easy access to files on the hard drive so that it can do its job and be done, right? The operating system might also provide common tasks that are done repeatedly by many programs so that we don't have to keep re-implementing the wheel, right? For example, accessing the file system, right? If you are responsible for in every single one of the programs you wrote for converting between the path to the actual location on the disk and then actually writing the code to read the file from the disk, it'd be a nightmare, right? If you had to do that for every single program. So the operating system provides that convenience for you, right? So that's the main ideas behind the OS. Yeah.
So what's the difference then when you say save the registers for X and there's already stuff of X in RAM? What's in RAM right now and what's in registers?
What's the difference between what's in RAM and what's in the registers? Well, like what's in the registers is whatever the program has currently decided to put into those registers to do, right? So whatever temporary local things it's working on in its computation. The other major ones would be like EIP, what instruction we're currently working on, and ESP, where's the stack at, right? But like the contents of memory for that process, right? They're going to contain the program's instructions, its text section, its data section if it has one, and then all of its locals and temporaries and everything else that's decided to place into memory, right? So like you can think about the registers are essentially what the CPU or what the process is doing currently, like right now. And then in memory, you kind of have like the entire process. So in a lot of ways, if you like taking 124A, you learn about caching, right? The registers are like a cache for the cache. The cache is a cache for memory, and memory is a cache for the hard drive, right? And at the end of the day, like your program is stored on the hard drive. Your process, the instance of it will be depending on if, with the virtual memory, part of it will be in memory and part of it may also be on the hard drive, depending who's in use when. And the cache is the more locally accessed, recently accessed things. And then the registers has like the most recently accessed things that it's working on right now at this moment. Hopefully that makes a little bit more sense, right? Because we can't fit the entire all of the instructions into the CPU at once because the CPU is very small in terms of how much data it can store, right? We can't fit all the data into the CPU. It's just what we can be working on right now. What instruction are we working on right now? And then like the EIP is going to help us figure out like what instruction we should do next because we can advance from there, either by a jump if we're doing a jump instruction, or just by going like +1 to get to the next one if it's not a jump instruction.
And it's like when you go to backspace, is that like an instruction for that program that goes into the instruction?
So your question is like when you type on the computer, how does that get resolved by the program you're working with? That's what we're going to talk about in a moment, which has to do with, in some ways, the interrupts. Because every time you press a button on the computer or click on the mouse, it creates an interrupt, which causes whatever program's running right now to like pause for a second. The operating system then goes and handles the interrupt. Like it gets the key that you pressed, and then it'll go give the key that you pressed, if your program was waiting for it, to that program. For example, like when you call scanf, right, your program pauses and waits for the user to finish entering input, right? The user's typing. Every time the user's typing, the operating system is kind of like saving those characters. And then once the user finally presses enter, the operating system knows that, oh, great, you're done, right? It then takes all that stuff that you've entered, whatever happens to be right now, and moves it over to your program, and then your program gets restarted and then handles that input. Same thing with mouses. But you can also make it, there are other ways of getting input besides scanf. That can be just like every time a key is pressed, run my program and do something with whatever I was given. And it'll just immediately give the key that was pressed to the program instead of like buffering all the input in that line and then passing it forward. And then this would be IO. Maybe IO dash, because slashes probably wouldn't work for the name. Let's be a path separator. New slides. So the first issue that we have to deal with is accessing the IO devices, right? Like how do we actually talk to them? How do we want to have them connected? This is in our book. This is chapter 8. Right, so IO devices have IDs, right? 0, 1, 2, 3, going up, right? Depending on like the actual ID depends on the IO port it is connected to. So if you're connected to port 0, your device's ID is 0. If you're connected to port 1, your IO device 1. If you're connected to port 2, your IO device 2. Right? So how do you guys have any ideas about how we might be able to access those devices, or ways that we could say talk to them? So there are two different techniques. One is called IO mapped IO, and the other is memory mapped IO. So let's talk about IO mapped IO. So in IO mapped IO, the IO devices and memory have separate address spaces. So if we go and we insert a table, so this might be for I/O. This would be like 0, 1, 2. But then we might also not like how this looks. It's so big. And then we might have memory. Right, so there's separate address spaces. There's I/O address 0, I/O address 1, I/O address 2, I/O address 3. There's also going to be memory address 0, memory address 1, memory address 2, memory address 3, and so on. The I/O address space tends to be a lot smaller than memory because there's a lot fewer I/O devices connected to your computer. Right? You have things like your Wi-Fi card, maybe like your Ethernet card, your monitor, your speakers, your mouse, your keyboard, a couple of USB ports, maybe like your HDMI port, a few other things, right? So like in general, like the I/O address space might be like a few dozen big in order to support all of the I/O devices that you have connected to it. Whereas like, you know, memory 2 to the 32 in terms of the number of elements, or 2 to the 64 in terms of the number of elements, depending on what the size of your CPU is. So how can you distinguish between the two? Right? So how can I distinguish between I/O address 0 and memory address 0? I/O address 1 and memory address 1 in terms of if you were implementing this. Right? What instruction do you use to access memory right now in Intel? What's the general one that you've used to grab a value from memory or put a value into memory? Move, right? Move L with the advanced indexing mode, right? So if you say move L something to address 0, it goes to memory address 0. If you move L something to memory address 1, it goes to memory address 1. Move L something to memory address 1000, it goes to memory address 1000, right? So if I have an instruction that allows me to say, put this thing into memory, how can I kind of like mimic something like that to allow me to access I/O devices? Just have another instruction, right? So separate instructions for accessing memory and I/O, right? In Intel, right, memory, like we said, is like move. Again, other instructions can, of course, access memory as well, like add, subtract, multiply, etc. But then for I/O, they have in for reading and out for writing. And they are literally called in and out. So if you say in from address 100, you're going to read from I/O device 100. If you say in from I/O address 3, you're going to read from I/O device 3. If you say I want to write a value to I/O address 5, if you out to address 5, you're going to put the value at I/O device 5. Right? So separate addresses. Does that make sense? So separate addresses, so separate instructions to be able to distinguish between the two, right? This might also cause us to have slightly larger buses, right? A bus is what? Remember buses? Chapter 2, what's a bus? It's what? It's just wires, right, that connect the different components together, right? So it might have a slightly larger bus because we need an I/O bus and a memory bus, right? to be able to access those two different things. So again, you have to add maybe a couple more wires to your computer to be able to support this type of system. So instead of splitting the address space up, what might be an alternative? Instead of splitting it up, what could we do? We could have them share the same address, right? That's memory mapped I/O, which is just I/O devices and memory share the same address space, but we just reserve some of the addresses for I/O devices. So you might say reserve like the first 100 addresses for I/O devices. So anything that goes to address 0, 1, 2, 3, 4, right? That would go to I/O device 0, 1, 2, 3, 4. Anything after that goes to memory. So we're out of time for today. We'll pick this up on Tuesday and wrap this up on Tuesday. Probably either finish on Tuesday or just only have a little bit of lecture on Thursday and then wrap up early then. Unless you guys have more questions and you want to talk about more things. I will see you guys either in office hours or on class next week.